In this screencast, we're going to establish the relationship between multi-particle systems and the constraints that are needed such that we can describe that as a rigid body. So recall that in earlier chapters we talked about multi-particle systems and we were able to apply Newton's second law to every single particle that's in the system. And so each particle has its own equation of motion, which is F is equal to ma, where we have applied to it at both external forces and internal forces. So Fi, j represents all of the internal forces between each of the particles within the system. And then we focused our attention on the center of mass of the system of particles, which we called G. And the location of the center of mass, G with respect to O, where O is fixed in the inertial reference frame, is given as the sum of the weighted position vectors of each of the particles divided by the total mass of the multi-particle system. And by looking at the center of mass, this gave us some really important relationships. The first is that the time derivative of the linear momentum of the center of mass with respect to a fixed point in the inertial reference frame is equal to the sum of the external forces. And this tells us that we can treat the translational motion of the center of mass, which we're calling G, as if it were a single particle of mass G, the sum of all the masses, when developing the dynamics for this system. And then we use the principle of separation of angular momentum to find two other expressions. The first expression is that the time derivative of the angular momentum of the center of mass with respect to point O is equal to the external moments of the center of mass about point O. Now, these two expressions from linear momentum and this angular momentum about point O, or with respect to point O, are saying the same thing. These are both translational equations of motion. But these particles can move around the center of mass, and that's what our second equation from that separation of angular momentum tells us, which is the time derivative of the angular momentum about the center of mass is equal to the external moments about the center of mass. So we get translational equations of motion from these two expressions, and then a rotational equations of motion for all the particles using this expression. Now these expressions will hold true for any system of particles. It doesn't matter how many particles are there. However, we noticed really quickly that these expressions became completely unwieldy when we had more than just a few particles, or if we didn't apply some severe constraints to the system to gain fewer degrees of freedom. And so this leads us now to our definition of a rigid body. And we've said before in this course that it's a collection of particles that are constrained so none move relative to each other. And so the constraint itself, or the series of constraints, is defined as the time derivative of the norm of the position vector between any two particles in a rigid body is equal to 0. So let's examine this constraint in a three-particle system. So the degrees of freedom of a system are going to be m is equal to 2n minus k. And this is for any planar system. And so if n is equal to 3, where we have 3 particles, then, and there are no constraints on this, then the degrees of freedom are equal to 6, because n is equal to 3, and k, our constraints, are equal to 0. So now we apply the mathematical definition of our rigid body to these 3 particles. And in saying that the distance between each of these particles isn't going to change at all. And this changes our system to where we have 3 constraints which connect each particle. So now, in a rigid body with 3 particles, k is equal to 3. And you can easily see that the degrees of freedom drop from 6 to 3. And we've stated this before intuitively, in which we have 2 translational degrees of freedom. So we can move to the left and to the right if we define our coordinates this way, and 1 rotational degree of freedom. And what you'll see is that we can apply any number of particles to this system, and if they share these same constraints, in which the position vector between them, the norm of the position vector, doesn't change, then the degrees of freedom in this system will always be 3. So we'll always have a satisfactory degrees of freedom so that we have 2 translational degrees of freedom and 1 rotational degrees of freedom. And so we can continue adding particles, and as n approaches infinity, then we obtain the geometries that we often recognize as shapes and as rigid bodies. And also recall our physical definition of a reference frame, that anytime we have 3 non-collinear points that don't move relative to each other, we can apply a reference frame. And we have more than 3 points in most rigid bodies, but that tells us that at minimum we need 3 points that are non-collinear, that don't move relative to each other in this multiparticle system, and we can apply a body frame B. And if we place the origin of the body frame B at the center of mass of the rigid body, then we can take advantage of all the relationships that we developed in earlier chapters on multiparticle systems, because now we've applied constraints to reduce the degrees of freedom to 3, 2 translational, 1 rotational degrees of freedom. And now we have these nice expressions, both translational expressions and a rotational expression to apply to the system.